AI does not live in the cloud. It lives in buildings that pull electricity like heavy industry. A normal server rack used to be a cabinet of computers. An AI rack is closer to a small electric furnace with networking attached. The bottleneck is no longer only chips. It is power, how fast you can get it, cool it, and keep it stable. Every chatbot answer starts as a load on a rail circuit. Somewhere, a transformer feels the request. Welcome to the Qoxum Knowledge Special. Today we take apart the AI data center, from GPU rack to power plant. If AI is the new factory, electricity is the raw material. That is why the biggest AI campuses now think like utilities. DOE says US data centers used about 4.4% of total US electricity in 2023, and could reach 6.7 to 12% by 2028. The same DOE report puts US data center electricity use at 176 TWh in 2023, with a possible 325 to 580 TWh by 2028. The IEA projects global data center electricity consumption to double to around 945 TWh by 2030. National totals sound abstract. The hard part is local. One campus can land on one utility territory, one substation, and one town. AI inference runs all day. Training can run for weeks. The data center wants power at 3 in the afternoon and 3 in the morning. Some workloads need to sit near users, cloud regions, or fiber routes. You cannot always move the load to wherever power is easiest. That is why power procurement moved from the facilities team to the strategy table. NVIDIA documents a DGX GB rack at about 120 kilowatts. That is not a normal office closet. It is industrial electrical equipment. An NVL72 rack is designed around 72 GPUs acting like one huge accelerator domain. The leap is density. Power that once spread across aisles can now sit in one liquid-cooled rack. Almost every watt that enters a server becomes heat. The cooling system is the receipt for the electricity bill. At these densities, air alone becomes too bulky. Liquid cooling moves heat out with less volume and more control. Training a large model is not thousands of independent computers. It is a synchronized machine that hates slow links and power glitches. After training, inference becomes the factory line, millions of small requests, always arriving, always using chips. Even when demand dips, a reserved AI cluster cannot simply disappear. Capacity has to be ready before the next surge. To a utility, the GPU hall is not magic. It is a large, fast-growing, high-reliability electric load. The power chain starts far upstream: nuclear, gas, wind, solar, hydro, geothermal, storage, or some mix of them. Transmission moves bulk power across long distances, but it was not built overnight or reserved for one new campus. Substations step voltage down and protect the system. For a giant AI campus, the substation is as strategic as the building. A transformer does not create energy, but it decides whether the energy can enter at the right voltage and scale. Switchgear, breakers, and relays isolate faults before a small problem becomes an outage. UPS systems buy seconds or minutes, enough time to ride through a blip or start backup power. Diesel or gas backup may protect uptime, but it is not the preferred everyday fuel for a serious AI campus. The building also consumes energy for cooling, pumps, fans, lighting, and losses. That overhead is why efficiency still matters. From generator to GPU, every watt passes through contracts, wires, transformers, protection systems, and cooling hardware. A utility cannot just plug in a gigawatt campus because a customer asks. It has to prove reliability for everyone already connected. Energy is the total bill over time. Capacity is whether the system can survive the worst hour. New loads need studies, equipment, permits, and construction. The calendar can become the limiter before the chips arrive. Large transformers are not commodity office supplies. They are heavy engineered machines with long manufacturing and transport chains. AI clusters also care about power quality, voltage stability, harmonics, ride-through, and fast protection. If a data center takes firm capacity, the grid still has to serve homes, hospitals, factories, and the next heat wave. That is why tariffs matter. Regulators ask who pays for new wires, substations, reserves, and risk. The gate is not the land purchase. The gate is interconnection, the right to connect a huge load without hurting the system. When grid power is slow, uncertain, or carbon-intensive, AI companies start acting like energy buyers, project developers, and sometimes utilities. Constellation announced a 20-year agreement with Microsoft to restart 3 Mile Island Unit 1 as the Crane Clean Energy Center. The important detail is matching power on the PJM grid. The deal is about carbon-free supply for the regional system, not a secret cable. Google signed with Kairos Power for advanced nuclear that could reach up to 500 megawatts of new 24/7 carbon-free power by 2035. Meta announced a 20-year nuclear agreement tied to the Clinton Clean Energy Center, securing 1,121 megawatts of emissions-free energy starting in 2027. Google also backed 115 megawatts of enhanced geothermal in Nevada, showing why round-the-clock clean power is becoming a data center product. The attraction of nuclear is not fashion. It is firm output, high capacity, low carbon, and always-on operation. Gas turbines can be faster to build, which is why they appear in emergency and bridge plans. But fuel, emissions, and permits still matter. Solar and batteries can scale quickly and reduce peak stress, but they need land, interconnection, and storage duration to serve the hardest hours. The new pattern is the Energy Campus, generation, storage, substation, cooling, and compute plan together. The best version is not leaving the grid. It is a partnership where the new load helps pay for new resources and flexibility. Cooling is not a side quest. Pumps, chillers, cooling towers, and dry coolers are part of the electrical design. Water impact depends on climate, cooling choice, power source, and whether you count on-site water or water used to generate electricity. Air cooling is simple and proven, but moving huge heat with air takes space, fan power, and wider aisles. Liquid cooling moves heat closer to the chips, which can shrink the thermal path and raise rack density. Some campuses will reuse waste heat for district heating or industry, but the economics depend on nearby customers and temperature. A power-heavy data center is also a land-use decision: transmission corridors, substations, generators, cooling equipment, and noise controls. Communities ask fair questions: jobs, tax base, water, noise, grid costs, and who benefits from the power build-out. The cheapest megawatt is the one you do not need. Better chips, scheduling, cooling, and software can slow the demand curve. Some AI workloads can shift in time or location. Training jobs can sometimes move around grid stress in a way hospitals cannot. Grid-enhancing technologies, reconductoring, topology optimization, and dynamic ratings can squeeze more out of existing wires. The long-term fix is new generation that fits the load: firm, clean where possible, dispatchable where needed, and connected in time. Storage cannot create energy, but it can move energy across hours and protect the grid from sharp ramps. On-site energy can help with resilience and speed, but it still needs fuel, permits, controls, emission strategy, and grid coordination. AI can also help the grid if operators expose the right workloads to demand response instead of treating every compute job as sacred. For cloud buyers, the compute product may soon include its power story, location, carbon, water, and grid impact. The winning AI campuses will not treat power as a utility bill. They will design chips, buildings, contracts, and grid upgrades together. First, AI is dense. A modern AI rack can pull power at a scale that changes the electrical design of the whole building. Second, the grid bottleneck is local. The question is not only how many terawatt-hours exist nationally, but where the next substation can be built. Third, AI companies now buy, finance, and shape power. Nuclear, geothermal, gas, Renewables, storage, and transmission are becoming part of the AI stack. Watch three numbers: megawatts of firm power, transformer and interconnection timelines, and how much load can flex without hurting users. The future of AI will not be decided only inside model labs. It will also be decided in substations, permitting offices, turbine halls, and cooling plants. AI needs its own power plant because intelligence at scale is physical. The cloud is becoming an industrial system. Thanks for watching. This is Qoxum. Knowledge stops being mysterious once you take it apart.